Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of Precalculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to do a last graphing problem on our introduction to graphing using calculus series. This is not including graphs of oblique or functions that have oblique asymptotes, nor am I using symmetry yet. So the full-blown graphing using calculus, that'll occur a little bit later. But for right now, let's finish this out. In this case, we're being asked to graph the curve f of x equals x times the square root of x plus 6, a harmless looking function. And for the most part, it is a harmless looking function, and it is a harmless function. So let's go ahead and go through our old school algebra. Y-intercept occurs when x is 0, which is 0, so we get 0, 0 as our y-intercept. Our x-intercepts, which if I could spell correctly would be nice. The x-intercepts occur when the y value is 0. And of course, we know one x-intercept is going to be at 0, 0, but we have another one. The second x-intercept occurs when that square root becomes 0, which is at x equals negative 6. So negative 6, comma 0 is also an x-intercept. If you're wondering how I did it so quickly, it was just because you have two objects multiplying to become 0, means either this first one is 0, so that's this case right here, or the second object is 0. That's this second case right there. All right, so those are our x-intercepts. So the algebra, easily done. Now we go to the domain, which is algebra 2, typically. Depends, I suppose, on where you learned it. And look for domain restrictions here. And in this case, this function definitely has a domain restriction. That radicand, the x plus 6, must be greater than or possibly equal to 0. Or in other words, x must be greater than or equal to a negative 6. So our domain is negative 6 to infinity. Now that we have that written down, and I have a bad habit of forgetting my domains. You've probably seen it in one of my previous videos already, where I forget what domain I'm working on. So it's kind of important that you keep track of your domain throughout. In fact, I'm going to highlight this so that I remind myself. That's very important. Remember that. Also, I'm going to start building a table of values off to the right. We have 0, 0, and negative 6, 0. So let me fill those in. So x versus f of x. I have 0, 0, and I have a negative 6, 0. Remember, negative 6 actually is in the domain, so we're perfectly fine there. Let's see, now we move on to precalculus. So we look at the vertical asymptotes if there are any. And the vertical asymptotes would occur if you had, for example, division by 0, or a function that has some type of weird domain issue, like a natural log, something like that. But in this case, we know square root functions don't have vertical asymptotes, and polynomials don't either. So this function actually does not have a vertical asymptote, so I don't really have to worry about investigating vertical asymptotes, because there's none on this. So these do not exist here. Horizontal asymptotes, those occur at the end of a function's domain. So the domain of this function, as I've highlighted, goes from negative 6 to infinity. So if you want to see if you have a horizontal asymptote, check the limit as x goes to positive infinity of your function, which is x times the square root of, what is it, x plus 6? Yeah. And you can see that'd be infinity times infinity or infinity. So definitely not a horizontal asymptote. So none, I should say. No horizontal asymptote, or does not exist. However, we do get a good idea of end behavior here. So I'm going to keep that around because that'll allow me to see what the end behavior of this graph should look like. Well, we're done with all the algebra and all the precalculus. So let's move into calculus. So f prime, it's a product of functions is what f is. So f prime is going to be the derivative of the first, which is just 1, times the second, plus the first times the derivative of the second. And then the second also has a function inside of it, but that function that's inside that square root is x plus 6, which has a derivative of 1, so you don't have to worry about that. So notice we're using a lot of our old skills to do this. Now remember, we're really looking for critical numbers here. Where does our derivative not exist, and where does our derivative become 0? Our derivative definitely does not exist at -6. So f prime does not exist at x equals -6. And while that's at the edge of our domain, it still is kind of an important piece of information, because that tells us that the curve likely goes vertical right there, or something to that effect. All right, let's see what else we have going on. F prime equals 0 when, well, when all this stuff right here is equal to 0. Well, that stuff is equal to 0 when a negative square root of x plus 6 is equal to x over 2 root x plus 6. All I did was set this equal to 0 and then subtract the square root of x plus 6 from both sides. Now I'll multiply both sides by 2 root x plus 6. So I get, this implies we have a -2 times the quantity x plus 6 is equal to x. Or in other words, -2x minus 12 is equal to x. Or in other words, -12 is equal to 3x. Or in other words, x is equal to a -4. I do want to double check that because I just think that it's important to do. So if I quickly double check that, yeah, I just paused the video so I could quickly double check the mathematics. That's perfectly fine. So we totally do have a critical value at -4 as well, or a critical number at -4, if you will. So I'll go ahead and quickly sketch out a line here for f prime. Remember, the edge at -6 is a critical number because the derivative doesn't exist there. And then at -4, we have another critical number where the derivative does exist, it's just 0. And now you plug in a value between -6 and -4 into the derivative. Let's see what the derivative is. It's right up there. I suppose it would have been nice maybe to combine these into a single fraction. So let's go ahead and do that. I'm going to multiply top and bottom of this guy by the square root of x plus 6. If you do that, you'll end up, actually, maybe I should say multiply top and bottom by 2 times the square root of x plus 6. So when you do that, you'll get 2 times the quantity x plus 6 plus x all over 2 root x plus 6. It's just a little bit easier when we take our second derivative, that's all. This will be a 3x plus 12 all over 2 root x plus 6. Again, double check my math, but I think that's correct. Yes, it is. Okay. So now what I'm going to do is just plug in to that last little expression there, this guy right here. I'll plug in -5. So f prime evaluated at -5. We have a -15 plus 12, which is a negative number on top, and the denominator is always going to be positive. So we have this. It's negative, so it's concave, or not concave, sorry. So the function is decreasing. Now plug in any number you want that's greater than -4. If you look at this, probably 0 is a very nice one. F prime at 0 is positive. That's all that matters. So I know that the derivative is positive in this region, so therefore the function is increasing. Now I'm going to take the second derivative. Oh, you know what I should do? I should probably add that point, -4, to this list. So let me add that point, which is -4, to this table. When x is negative 4, what does the function turn into? It turns into a negative 4 root 2. Okay, I could keep it like that for now. That's perfectly fine. And by the way, that is going to be, it goes from decreasing to increasing. So decreasing to increasing, that's a local min. So I'm going to make that little note on my table as well, just in as many spots as possible. Just state where your mins are and your maximums are. What else do we have here? Second derivative. So the first derivative is this guy right here, and that's the one I'm concentrating on when I start working with my second derivative. Okay, so second derivative, I'm going to be moving back and forth a little bit. The derivative of the numerator is 3 times the denominator, which is 2 root x plus 6, minus the numerator, 3x plus 12, times the derivative of the denominator. Well, that's times 2 times, because 2 is just the constant. The derivative of that square root is 1 over 2 root x plus 6, and the derivative of x plus 6 is 1. It's a multiplication sign right there. And this is all over that denominator squared. So 4 times the quantity x plus 6. Now I'm going to go ahead and multiply both numerator and denominator by the square root of x plus 6, noting as well that these 2's cancel. So multiplying top and bottom by the square root of x plus 6, or in other words, the half power of x plus 6, you will get the following. 6 times the quantity x plus 6 minus the quantity 3x plus 12, all divided by 4 times the quantity x plus 6 to the 3/2 power. We're just adding a half to all the powers of x plus 6. All right, and finally cleaning up. Let's see, I have a 6x minus 3x is 3x. I have a 36 minus 12 is a positive 24. And this is all over 4 times the quantity x plus 6 to the 3/2. You can obviously see this second derivative is undefined at -6. Technically, you could also factor out a 3 out of the numerator. That's not going to really help in this situation, but you could have done it. But I'm not going to do it. And now I'm going to go ahead and draw out that number line. Make the little note here that, again, it's not defined at -6. There's f double prime. The numerator becomes 0 when x is -8. So that's actually outside of our interval. I don't have to worry about that. That's actually very nice. Again, just want to say it out loud. Like if you were to set f double prime to equal 0, well, f double prime equaling 0 implies 3x plus 24 has to equal 0, which implies that x would equal -8. But -8 is outside of the domain of this function. So we don't have to worry about that numerator ever becoming 0. So there are no critical numbers on the domain of this function. Well, okay, other than -6 for this, for the first derivative, which is where the second derivative becomes 0 or does not exist. So let's test any point we want greater than or equal to -6. And I'll just plug in 0 and you'll get a positive number. So this means our curve should always be concave up. Always, always, always. We don't have any other information. That's pretty good. Let's go ahead and quickly draw out the 2 number lines up above so I can use them to scale. All right, I labeled everything. I did the same thing I did in the last video where I drew my 2 horizontal lines there for one for f prime, which I didn't label, but there it is, and one for f double prime. And this just allows me to kind of see where points should fall relative to the axes. I'm going to now plot the points in the table, which are 0, 0, and -6, 0. Let me go ahead and do that. That's actually pretty easy. 0, 0 obviously is right there. And -6, 0. I'll just move this over here and let me find where my, there it is. So to see if I'm actually vertical. -6, 0, roughly right about there. I'll even label that -6, 0. And again, I should probably label this 0, 0. The bad thing about labeling, or the tough thing about labeling early, is that you might have to draw through your labels, which is always a pain. But if you want to hold off on labeling until the end, that is absolutely fine. But if I do that, let's just say I do, then I often forget to label at the end. Let's see. We also have 4 comma negative 4 root 2. Negative 4 root 2 is roughly 5.6, 5.7, somewhere in there. So negative 5.7 roughly. So I'll go ahead and maybe scale down. I'll just pretend as though a specific height is negative 5.7. I'll say it's right about there. I can actually turn this off now. So this point is negative 4, comma negative, what was it, 4 root 2? Now I'm going to look up above. The function where it starts, which is at negative 6, comma 0, good thing I erased that, it's going to decrease but be concave up. So this is concave up but decreasing. And then it's going to continue to be concave up but start to increase at x equals negative 4. So this is going to take a little bit of artwork here. This is why, by the way, I hash things out like this, is so that I can erase where it didn't look good, where I kind of missed or something like that. And then it's going to increase until you get, well, actually it's going to be concave up and increasing forever. So it just wants to eventually get to this and then climb past it. So I'm just going to do it like this. That's a pretty good increase in concave up. And it's going to continue to be concave up and increasing forever. So it's going to do something like this. And by the way, that should make sense because it matches our end behavior, that as x goes to infinity, the function's going to climb to infinity. And that's exactly what's happening. So this is the graph right here, whoops, of our function x times the square root of x plus 6. A very accurate graph of that function. All right, that wraps it up for all the graphing, kind of the intermediate graphing videos. How's that?
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.